In the second example, we're going to look at that same cantilever beam that we had, but we've added in an additional force, this P here, which is halfway along the beam. So again, we want to draw our shear and moment diagrams. You see that they are lined up below the beam itself, the free body diagram for that beam. And we also want to come up with equations for the shear and moment as a function of x. The first step in doing this is to do a cut. We'll take our first cut at this location, and that location we'll call cut 1. And cut 1 is located between x is equal to greater than or equal to 0 and less than L over 2. Now we will draw the free body diagram for that cut. Okay, now that we have the free body diagram drawn, you see, make sure that you're very consistent in these directions for these forces and the moment. This is the standard or the convention that we will be using. Okay, so we can start doing our equations of equilibrium. We'll solve for F in summing forces in the y direction. We have a minus P minus VC1. We find out that VC1 equals a minus P. Next, we will do a summing our moments at the cut 1. We have MC1 plus P times X. MC1 equals A minus PX. Evaluating that, we find out that at X equals 0, our MC1, our cut 1, is equal to 0. And at X equal to L over 2, our MC1 is equal to a negative PL over 2. So just real quickly, this is our equation for our shear and moment as a function of x between 0 and L over 2. Now we'd like to take a second cut. I'm going to take that here, cut 2. And notice that I take it after this discontinuity or some change, which is this concentrated load. So we always kind of look where we want to take these cuts. So this is the second cut. That cut, again, is cut 2, and that is between x is equal to our L over 2 and up to L. So that is our range. Now we need to draw the free body diagram for this cut, and I'll draw that over here. So here's the free body diagram. The next step that we want to do is sum forces at in the y direction at our cut, or on the whole diagram, excuse me. We have a minus P minus VC2. That gives us our VC2 is equal to a minus 2P. So there's one equation for our function of x for the shear. The last part is to sum moments at the cut 2 equals 0. That's our MC2 minus P times x. Oops, that should be a plus. Sorry, that's a plus positive moment. And then we have plus P times this moment arm here, which is x minus L over 2. We can solve for MC2, and that's just a little bit of algebra here. Okay, so now if we evaluate this, we see at x equal to L over 2, we will find MC2 is equal to a minus PL over 2. At x equal to L, our MC2 is equal to a minus 3 PL over 2. All right. And then we will graph this onto our shear and moment diagram. Okay, now so if we graph this, we look at the first value from L to L over 2. It starts out at a minus P and stays constant. At L over 2, it jumps down to this value of negative 2P and stays that way to the end. So if we look at that, if that comes down here, and that's lined up here, we see that that's where that's happening. This again is at L over 2. We should label this as minus P, and this is minus 2P. Last, we need to put in the moments. The moment starts out at 0 and goes to a value of negative PL over 2. So and it's a linear slope for that. So this is a negative PL over 2. And it ends at this value of negative 3PL over 2. So then it comes down to some other slope. It changes negative 3PL over 2. Okay, so that's how you do the shear and moment diagrams and how you come up with the equations in X along the beam.